In our understanding of equilibrium, we've now had an opportunity to look at things like an equilibrium constant and what that means. We've had a chance to look at an equilibrium expression and the ratio that is created between my products and my reactants once a reaction or once a system achieves equilibrium. We've also had a chance to start solving the question of, so once equilibrium is established, what are the concentrations that we have of each of our varying reactants and products? What we haven't spent any time looking at is from a more qualitative perspective. If we didn't really need to get into, well, exactly how much, if I just wanted to know in general how much of a substance I would have or which way would a reaction shift, what we haven't spoken about yet is this idea of how can I generally predict what will happen to a system that is at equilibrium when we apply a stress. And so this idea of a qualitative descriptor of what happens when systems at equilibrium get stressed is known as LeChatelier's Principles, LeChatelier's Principles. And what we're going to be doing in this section is we're not going to actually be solving for a particular value, but we're going to be able to understand what happens when a system is stressed. How does it respond? I think the best way to think about it is, imagine, if you will, that you were sitting there at your desk, at your table, whatever it is, watching this video, and someone were to now come up to next to you and start poking you, right? And so let's just say, sake of argument, that they start to apply this stress over here on your right side. So they're going to start pressing, right? Well, what's your natural instinct? If I were to start poking you from one side, you're automatically going to shift away from the direction of the stress. Likewise, if I came at you from the other direction, if I started poking you this way and I started, hey, and I started jabbing you this way, well, same thing. If you come at me this way, my tendency is immediately to shift away from the stress. And that is what every equilibrium is going to attempt to do. If we go back to our example of the wildebeest and the lions, remember, we could add stresses to that equilibrium. There could be a drought. There could be a year of excessive rain and a bunch of extra grass. We could have a bunch of poaching. Whatever stress we want to introduce, remember that as the stress was introduced, the equilibrium would shift with the goal of reestablishing whatever that balance was. So it's not like once a stress is applied, that's it, everything's out the window. It's more along the lines of that when you apply the stress, okay, stuff's going to happen, but the system is going to work really hard at trying to reestablish the exact same ratio. Now we have three factors that will affect that will cause an equilibrium to shift to try to reestablish itself. There's three things that we can do. There's three stresses that we can apply to a system that will cause stuff to happen. Number one, we can change the concentration of either the products or the reactants. So changes in concentrations of product or reactants will actually cause the reaction will want to produce more products, or it may want to produce more reactants, depending on what you did, how you stressed the system. We can also change the pressure, and I'm going to put air quotes on that, in gaseous systems. Now, for 1 and 2, what we're doing in both of these instances is that we're in essence going to be changing the concentrations. And I know you're looking at number 2 and you're going, wait, how did I change the concentration number 2? But we'll get there, okay? But what we're doing is that in essence in 1 and 2, we're changing the concentrations or amounts of reactants or products. And so in changing that, it's as if I am altering the reaction quotient. So for 1 and 2, we're going to use our analogy again of Q, and we're going to ask the question, how does Q affect K? And finally, in number 3, when we change the temperature, it is only by changing the temperature that we actually alter the equilibrium constant value. We change where the equilibrium lies. In other words, if it's supposed to be 50-50, when I alter the temperature, now I get one side or the other side more highly favored, depending on what the change in temperature did, which side it kind of promoted and caused more of that side to occur. Now, there is one thing that we have spoken about that will have zero effect on an equilibrium, and that is the addition of a catalyst. Now, you might be sitting there going, wait, doesn't a catalyst speed up a reaction? And the answer is it does. So the catalyst is going to get us to our equilibrium values faster, right? It'll get us to whatever the equilibrium constant or the ratio is faster. It will not alter where equilibrium lies. So for this whole section, as long as we're talking about equilibrium in any facet, you are never concerned about catalysts, because what we're looking at is once equilibrium is established, where does, which side is favored? Where does my equilibrium lie? So that's going to be our focus.
So we take it one step at a time, one tick at a talk, and you'll be there in virtually no time.